Okay, welcome back from the break. This is week 9. The topic for the week is graph. So this is where we are. We are at the third and the final data structure, which is graph. As mentioned before, this is one of the most powerful and most expressive type of data type. We're going to see a lot of examples about how we can use this particular data type to capture a lot of real-world applications. So we're going to do 3 things today. First, we'll be covering the graph data type following very similar styles of introduction, going over the high-level introduction and all the way to lower-level implementation details. Second is very similar to what we did last week. Last time when we introduced the tree, well, we are going to talk about how we can systematically exploit the data element we see in the graph. And final part, we're going to use graph as the foundation to introduce more advanced usage of the graph in addressing important real-world problems. Okay, so this is one of the most typical type of graph you will see using the representation of the land transport. I think what you can see over here is one of the more complicated subway structures, and this is from London. Second example over here, this is one of the most famous social network. This is right after September 11th terrorist attack. After that, U.S. intelligence agency actually analyzed all the communications between different terrorists that were involved in this attack, and they did observe if they were able to monitor the communication channels they use, they can clearly see a communication social network among all those terrorists who are involved in the attack. Second part is still another example of the social network. This is another criminal act. This is the on the investigation of how Enron scandal unfolded. Enron, if you look it up, this is one of the most infamous corporate crime in the U.S. history. A lot of individuals in the higher up hierarchy of the companies are involved, and from the analysis of this email chains, you can kind of see who are actually involved in this particular business crime. Right. Final part is the social network. By looking at the Hollywood artists, right over here, you can see that all the actors and also actors who actually appear in the same film. If you connect all of them together, again, it forms the foundations of a social network. And from this, you can kind of see that who is kind of the center of all the important films, who actually work with a lot of different actors or actresses. So in the area of social network, one of the most well-known finding is what we call the small world phenomena. The name of this small world phenomena actually comes from Dr. Stanley Milgram. He's actually he's not a computer scientist. He's a psychologist by training, but in the very early stage, very early on, before even the invention of email or any social network software, he tried to investigate how individuals are connected to each other. How many social interaction would be required to connect any two individuals within the United States. So the following box that you see from here, this is actually the social network experiment he has conducted. So he called it the small world experiment. He essentially tried to, by using the traditional mail, postal mail, and he just on the envelope, he put in a name that's somewhere to the east coast of the U.S. That's in the city of Boston, Massachusetts. So he just randomly sent out all these postal mails to some individuals in the city of Omaha, Nebraska. This is somewhere in the middle of the U.S. So instruction is actually very simple. If the recipient of this particular envelope actually know the intended recipient, the target person over here. In the experiment, this is the target person. Then the individual will actually send directly this particular envelope to the final destination. But if this particular recipient, which is the most cases, this particular recipient doesn't know the target person that's written down on the envelope, he will try to write down the next person on the envelope. And then that will be the person he think that most likely he or she will know the target person. So by tracking all the names and addresses that all these participants put on the envelope, he can then, by collecting all this envelope, analyze the numbers of hops it would take for any individuals or region from somewhere in Nebraska or Kansas, somewhere in the center of the U.S., to an arbitrary individual in Boston. So the next page over here is one particular example. On the left-hand side over here is actually the origin, right? This is Omaha, Nebraska. On the right-hand side in the blue circle, this is Boston, Massachusetts. So again, over here, the very first recipient of the envelope, if he doesn't know the blue person, he will forward it to like somewhere to the closer to the East Coast. Maybe this is somebody he know that's to the easternmost states in the U.S. And again, this guy, the second guy over here, he will look at the target person to see whether or not he actually knows this guy. If he doesn't, he will forward even further to eastern states. And gradually, as you get closer and closer, you may or may not get into the city and actually find the final individual. So very simple experiment and a very ambitious experiment as well, because this is quite a large span between these two origin and destinations. But the surprising finding that he gathered is that actually the success rate is reasonable. Out of close to 300 mails that he sent out to different individuals in the Nebraska state or Kansas state, close to 20% of all those mails eventually reach the final destination. And the average pass doesn't really take very long. It's only take a hop of 5 or 6 before eventually the mail get delivered to the final destination. So this is the origin of this famous phrase that come from this particular out of this particular experiment. It's called 6 degrees of separation. It basically means that between any two arbitrary individual in the United States, you only take about 5 to 6 person in between to connect them. So of course, I mean, with today's social network services online, it can be Facebook, it can be LinkedIn, it can be Twitter, so on and so forth. This social network is even closer than before. So I mean, people did a very similar analysis on any arbitrary two individuals by using the Facebook data, and they discovered that the average pass length now is only around 3. It can be even shorter if you use even the latest data that's available, right? But that's just a demonstration about how you can actually use the graph data structure to analyze the relationship between people. Okay, so how do we do all that, right? So this is the abstract view of a social network or any kind of network, actually. The very first type of graph we're going to introduce today is what we call the directed graph. It's called directed graph because if you look at all the edges that's inside this particular graph over here, they actually have directions, right? You see they are directed. That's the reason why we call this graph directed. So this here are some of the notations. Usually we use G to represent the graph itself. And the graph usually consists of 2 important sets. First is the vertex, all the nodes, in other words, from A to F in this particular graph over here, and the set of edges that's connecting all the vertices. So internally, if you want to represent, for example, the graphical relationship that we've seen in the previous slides, there are two ways of doing that. Again, depends on your application. You can either do it by using agency list over here, right? Or you can use agency matrix. So agency list, if you look at it specifically for each individual vertex, we simply list down the other vertices that this vertex is connected to. For example, over here you see that for vertex A is connected to B, is also connected to C, right? And again, remember this is directed. So the fact that you have an edge connecting vertex A to B doesn't mean that you have another edge connecting from B to A. This is asymmetric. And on the right-hand side, right, this is usually applied in the mathematical formulation if your purpose is to perform any type of computation on the social network. This is what we will do. We use 0 to represent that there's no connection at all. And we use 1 to represent there's one edge existing between the front nodes, which is over here, front vertex, and the two vertices over here. Right over here, for example, if you have 1 in the matrix, it means that you actually have one edge connecting from A to B. Right? So if you look at the information stored on the right hand side should be exactly the same as the information stored on the left hand side. Here we see that A is connected to B and A is connected to C. In the matrix, our expectation is that because of that, you should have 1s in the columns of B and also the column of C. Okay, so this is two different underlying representation that we can use to represent the graph. So in terms of connectivity, we actually have the following different important definitions. So first, two properties are defined for individual vertex. So for a particular vertex, we can define the in degree, right? This is essentially counting the numbers of edges that's going into a particular vertex. And also, very similarly, we can count numbers of numbers of edges that's going out of a particular vertex. This is what we call the L degree. These two information combined together can tell us for a particular vertex how connected it is based on the incoming links and the outgoing links. And the third terminology over here, which we use very often, probably not this week, but we'll use it very often in a lot of different places in the next week's content, is paths. Right? So inside a particular graph, we can actually collect a sequence of vertices. They are all connected one after the other. This is essentially, you can imagine, that's the paths that can form. For example, if we use the graph to represent the social network, that would be the ways where you can connect from one individual to another individual. Or it can be from, if we use the graph to represent transportation network, then the paths will represent ways to travel from one origin to another destination. Simple paths is essentially a path, but you see this special requirement over here. We require that all the vertices that's inside the path appear only one time, right? Because the paths contain only unique set of vertices. It means that a vertex cannot be visited for the second time if the path is simple. Finally, we have a special type of path. It's called a cycle. Simply means that you begin and end your path at the same vertex. Okay, so these are some of the very simple definition of terms that we'll be using throughout these 2 weeks. All right, so after directed graph, we also have the graph that doesn't contain directions. You can see from the drawing of the edges, you don't see any direction at all. So which basically means that if you have one age connecting A and B, this relationship then will be mutual, right? So an age between A and B basically means that A can go to B and B can also go back to A. So if you look at the agency list, now we see symmetry, right? So A inside A's agency list, you can connect to B and C. So if you check B and C, they must be connected back to A as well, right? So this is one example, right? So every scene, in other words, if you look at the agency matrix, they are symmetric, right? All these numbers over here, you see that along the diagonal line, you have AB, then it basically means that you have BA as well. You have AC, it means that you have CA, right? So you have BC, then you have CB, right? So the symmetric relationship is across the diagonal. Okay, so this is the second type of the graph. We call it undirected graph. So this is basically the abstract definition of this particular data structures. The next we'll be seeing the more detailed implementation details. As always, if you want to go over the hands-on exercises, experimentations, you can refer to the third chapter of our handout. You can again download it from the eLearn. So these are the properties and also the methods that are available to the graph data structure. So again, the very first function over here, this is the function that allows you to create an empty graph. It contains nothing. So inside the graph, it initially, of course, contains no vertices at all. But as you add more and more vertices by using the next function over here, you can actually grow the content of this particular vertex. This vertex is essentially a list that contains all the vertices that's contained within the graph data structure. So you can add more and more vertices. You can delete the vertex as well. You can, after you insert the vertex into the graph, you can also specify the ages in between multiple pairs of vertices by using the add age method over here. Weight over here, this particular parameter, when we add the age, is optional, right? So initially, at least for the previous two examples that we illustrated in the directed and undirected graph, the weights are always 1, right? Simply representing either you have an age, in which case your weight is 1, or you don't, in which case you will have 0 for the agency matrix. Finally, of course, you can add the age. You can also delete the age by specifying origin and destination. And vertex, this is basically used within the graph itself. It itself is an object type, right? So you can essentially use a unique label to represent a particular vertex. So agency list, right? This is following the data type, the representation of the graph that we have earlier, right? So for each and every vertex, if this particular vertex is being used within the graph, you can actually specify the list of some other vertices that it is connected to. The final property, this is the property we use to track whether or not this particular vertex is visited or not. Later you'll see that we use this particular property when we traverse the graph. Okay, the final page over here is an extension of the graph that we see on the previous page. And on the previous page, the graph is assumed to be directed, but based on that, we can also define an undirected graph. The only thing that's special over here is that when you insert an age between a vertex V1 to V2, for example, V1, V2, this particular age cannot be unidirectional. It has to be bidirectional, right? So that's the only difference between directed and undirected graph. The final method, you can use a view graph. You can experiment a bit to actually show the layout of the graph according to the coordinate that you specify on the previous page. Okay, so this is the very high level introduction of the graph and a very brief overview about all the methods that are available in the Graph Lab Python file that we have provided in this particular week. All right, so we will stop here and then you can rest for a while and we will begin talking about different methods of traversal.